Let's talk about this review problem concerning a continuous random variable. First thing we need to do is to verify that this is indeed a probability density function, or PDF. To verify that little f of x is a probability density function, we have to do two things. We have to verify that the function is non-negative, at least between 1 and 3, and we also have to verify that the integral between 1 and 3 is equal to 1. It is clearly a non-negative function if x is between 1 and 3. We have that x is positive, and so x cubed is going to be positive, 5x is going to be positive, and so x cubed plus 5x is positive, and so x cubed plus 5x over 40 will be positive. So clearly the non-negative component is correct. To check the integral is correct, we do the integral from 1 to 3 of x cubed plus 5x over 40 dx, and then do the integral. So that'll be equal to 1 over 40. And then the antiderivative will be x to the fourth over 4 plus 5x squared over 2. And I evaluate my endpoints between 3 and 1. And so that will be equal to 1 over 40 times 81 over 4 plus, plugging in 3 here, we get 5 times 9, which makes 45 over 2. And then plugging in 1, we get 1/4 plus 5 times 1 squared for 5 halves. And so that will be indeed equal to 1, just simply doing the calculation. So that is part number 1, just verifying that the function is indeed a probability density function. For problem number 2, find the probability that x is greater than or equal to 2. Well, in this case, if we didn't have this constraint, we would integrate from 2 to plus infinity, where x is greater than or equal to 2. However, because of this constraint, I don't integrate from 2 to plus infinity. Instead, I integrate between 2 and 3. So the calculation will be actually fairly similar to what we just did. I will not be integrating between 1 and 3. Instead, I will be integrating between 2 and 3. And so I also would have a 2 here. And so the calculation will look very similar to what we just did, except I have to plug in 2 for my left endpoint instead of 1. So plugging in 3, I get the same answer as what I had before. Plugging in 2, I would get 16 to the 4th, or excuse me, 2 to the 4th over 4, so 16 over 4. And then plugging in 2 here, we get 5 times 4 for 20 over 2. So this is the probability that x is between 2 and 3. And so we plug into the calculator, and we get our answer of 0.71875. Now clearly for a problem like this, we must get an answer that is between 0 and 1. It is a probability that we're looking for, and so the answer that comes out must be between 0 and 1. That's not going to be the case for the integrals that we're going to do in problems 3 and 4, as we'll see. Problem number 3 is to find the expected value of x. So the way that we find expected values when I have a continuous random variable is that I integrate over the entire range from 1 to 3, but I take x times the density function x cubed plus 5x over 40 dx. And this will be the expected value of x, which is also symbolically denoted by the Greek letter mu. So this will be the average. So before we integrate, let's simplify this. Let's pull the 1 over 40 out. And also let's multiply by x, so I have x to the 4th plus 5x squared dx. Doing the integral, we get 1 over 40 times x to the fifth over 5 plus 5x cubed over 3 from 3 to 1. And so we plug in, we get 1 over 40. First we have 3 to the 5, which is 243, divided by 5. Then plugging in 3 for this one, we get 27 times 5, and 27 times 5 is 135, divided by 3. So that's the right endpoint. The left endpoint, we plug in 1, which is a little bit easier. We get 1 to the fifth over 5, plus 5 times 1 to the third over 3. And so we do this calculation, we plug in, and we get our answer out of 2.293 repeating. And it's perfectly okay that this answer is bigger than 1, because this is not a probability, it is an expected value. So I expect the expected value to be somewhere between 1 and 3, because the random variable must be between 1 and 3. Okay, so let me write that up here for safekeeping, that the value of mu is equal to 2.293 bar. For part 4 here, we have to find the expected value of x squared first in order to get the standard deviation of x. So let me clear out the space down here. To get the standard deviation of x, the first thing that we get is the expected value of x squared. We already have the expected value of x, and so next thing we need is the expected value of x squared. So this will be equal to the integral from 1 to 3 of x squared times 1 over 40 times x cubed plus 5x dx. So this is equal to 1 over 40 times the integral from 1 to 3 of x to the fifth plus 5x cubed dx. So we do the integral. We get 1 over 40 times 1/6 x to the sixth plus 5/4 x to the fourth evaluated between 3 and 1. That is equal to 1 over 40. Okay, plugging in 3 to the sixth divided by 6 is 729 divided by 6. Plugging in 3 here, we have 3 to the fourth is 81 times 5 for 405. Divided by 4. Plugging in 1, we get 1/6 plus 5/4. And then plugging into the calculator, we get that this is equal to 5.53 bar. So that is the expected value of x squared. Finally, to get the standard deviation of x, we use the values that we just got. So the standard deviation will be equal to the square root of the expected value of x squared, which is 5.53 bar, minus the average, which we've already found to be 2.293 bar, quantity squared. So the expected value of x squared, that goes here, and the mean, which we found already, that goes in the second slot, squaring that, and we subtract. The thing under the square root must be positive, or at least not negative. If the thing under the square root is negative, then something went wrong. Okay, so finally we plug into the calculator, and so we get that the standard deviation is 0.524, excuse me, 0.5234, rounded off to 4 decimal places. So that is the standard deviation of x. Next, we'll take a look at the cumulative distribution function for the random variable. So I'm going to clear off some space so we have room for that. Okay, let's remind ourselves that what the cumulative distribution function is. The definition of the cumulative distribution function is that f of x is equal to the probability that the random variable capital X is less than or equal to little x. In our case, this will actually have 3 parts. First, so let's deal with the easy parts first. The first easy part that happens is if little x is less than 1. So let me draw a little schematic down here. So there's 1, there's 3, and suppose little x is over here someplace. The random variable capital X is guaranteed to be between 1 and 3 someplace. And little x is over here. So no matter where capital X is, it is guaranteed to be to the right of little x. So capital X in this scenario cannot possibly be to the left of little x, and so the probability of this event is going to be 0. So that's one extreme. The second extreme is going to be the case where x is greater than 3. So for this picture, we'll take this off. And what I have is that little x is now over here to the left of 3 someplace. Excuse me, to the right of 3 someplace. So capital X must be between 1 and 3. Little x is over here, so we're guaranteed that no matter what, capital X has to be less than or equal to little x. And so we are guaranteed, in this case, that capital X is less than or equal to little x. And so if x is greater than 3, then the chance of this event is 100%. So those are the 2 easy cases. The one case that isn't so easy is the case in the middle, where x is something between 1 and 3. Okay, so the chance that capital X is less than or equal to little x. For this one, we now just simply integrate. The probability that capital X is less than or equal to little x. That's saying that capital X is somewhere between 1 and x. And so I integrate the PDF, and I use some other letter of the alphabet because little x has now been reserved as the right endpoint for doing this integral. Okay, so I do the integral, and I get 1 over 40 times t to the 4th over 4 plus 5t squared over 2 evaluated from x to 1. Okay, so plugging in, we get x to the 4th over 4 times 40, which makes 160. And I'm going to put everything over 160. And the next part's going to be 10 fourths, or 5 halves, x squared over 160. Then what I get when I subtract 1. So when I subtract 1, I have minus 1 minus 5 times 2 for minus 10. So doing a couple steps quickly, we get x to the 4th plus 10x squared minus 11 over 160. And so that's the answer that would go here to describe the probability that capital X is less than or equal to little x if x is between 1 and 3. So there's our answer. Let me clear off a little bit of space here, but we're going to save that because we're going to need that later. Finally, for problems part 6, we want to find the 80th percentile. Let me save this and move this up because we're going to need that for later. Find the 80th percentile. In other words, so let me draw the picture just to give an idea of what we're looking for here. So to find a percentile, this time the area is given. So the graph of x cubed plus 5x over 40 from 1 to 3, I don't need to have a terribly exact picture, but it goes something like this. And the question is, find the value of x so that the area under the curve is equal to 0.8. That's what it means to be the 80th percentile, whether I'm under the bell curve or I'm under something else that isn't the bell curve. So I need to have the integral from 1 to x of the density function, which in this case f of t dt, to be equal to 0.8. Okay. The thing on the left-hand side, I can directly integrate this. That would work. However, I already did this for part number 5. That is the density, the cumulative distribution function, or CDF, capital F of x. And so that is exactly what we just did over here. So let me just copy that answer. I need this to be equal to 0.8. I've already done the calculus. I can reintegrate this if I wish, but there's no need because I've already done it once. So it's just a matter of solving for x in this algebra problem. So I've now reduced the problem to something that is strictly algebraic. Okay, so now we just solve for x and turn the crank. So let's multiply, clear out the denominator. We have x to the fourth plus 10x squared minus 11 is equal to 160 times 0.8, which is 128. So x to the fourth plus 10x squared minus 139 is equal to 0. And so this is quadratic in form, so I use the quadratic formula. So x squared is equal to negative 10 plus or minus, more on that later, the square root of 100 minus 4 times 1 times negative 139, and that works out to be plus 556 divided by 2a, so 2. So that gives x squared is equal to negative 10 plus or minus, we'll get to that in a second, square root of 656 divided by 2. Okay, now which is it, plus or minus? Well, in this case, x squared, well, that's clearly a positive number, at least not negative, and so there's no way it can be minus here. So I'm going to get rid of the minus sign. X squared has to be a positive number, or at least not negative number. If I put a negative there, I get something that's negative, so that cannot happen. So x squared's got it. I have to choose the positive entry here. So x squared is equal to, I can pull a 4 out of the square root, and I end up with negative 5 plus the square root of 164. Okay, then finally to solve for x, we get x is equal to, well, if x squared is equal to this, then x is equal to either plus or minus the square root of negative 5 plus the square root of 164. Now once again, which is it, plus or minus? Well, in this case it has to be plus. The reason is because x must be something between plus 1 and plus 3 in my picture. So the negative solution there is also extraneous, and so I will just simply get rid of it. And so there is my answer. X is equal to square root of negative 5 plus the square root of 164. and plugging into a calculator, that gives us x is approximately equal to 2.72207. So the setup for solving for a percentile is we do this integral, or else we use the CDF. Either is they mean the exact same thing. And then we use algebra as necessary to solve for x. In this particular problem, the quadratic formula was necessary. For other problems, some other technique might be used depending on what this left-hand side looks like.